the beginning, I must thank the organizers, the Bongaigaon branch of Assam Academy of Mathematics, for giving me this opportunity to share few ideas about some problems for those some students, those who are going to appear for IUKM this year. Am I audible, all of you? Please let me know whether my audio is clear.
Fine, no problem.
Okay. Thank you so much, sir. So it's really an honor for me to share few idea about Olympiad related problems. As Sahib has already mentioned that I am in association with this Assam Academy of Mathematics for many years, since 2008. So it is approximately 14 years I'm touch with Assam Academy of Mathematics, and obviously dealing with the Mathematics Olympiad and related activities. So thank you. Now today I'll be discussing this Diophantine equation, and I have seen there's some questions of this type, that is Diophantine equations, are asked in Mathematics Olympiad. That is my observation, and there is also an important topic to be discussed, what I feel. But some concepts are associated with these equations related to set and the number theory. Yes, so I'll try to discuss these things in a simple manner so that school students can understand. Before actually starting, may I know how many, if all the students are from English background, I mean English medium, so that I can continue in English, or if needed. Okay, thank you. Yes, I think all the students are up to class 11.
Yeah.
Okay, thank you. Okay, let me start now. So Diophantine equation. Now, if I talk about the basic definition of this equation, is that now if an equation of the form, say f of x1, x2, xn equal to 0, where f is a function of n variables, or where n is greater than or equal to 2, is termed as a Diophantine equation. Now, if f is a polynomial function, with integral coefficient, that is the coefficient in this, for this polynomial, if the coefficients are integers, integral coefficients, then this equation 1, if I mark this equation as 1, then this equation is called the algebraic Diophantine equation. Algebraic Diophantine equation. If this is a polynomial function and the coefficients of the polynomial are integers. So, for example, we can consider this equation, say a1 x1 plus a2 x2 plus a3 x3 x3 plus say an xn equal to 0. So this is a linear equation. This is a linear Diophantine equation. But if it is not necessary that it should be linear always, it may be non-linear. The coefficient, the power of x, the variables may be more than 1 as well. So in general equation is given by this one. Now there is a classification or a particular case when this equation is linear. So now the solution of these equations. Now, first of all, whether in order to solve this equation, first of all we need to understand whether this equation has a solution or not. Now, if this equation is a general equation, and this equation is a particular equation. So I have some say m1, m2, or some m3, etc. So here all these powers of variables are integers. So it's a polynomial, simple polynomial, and a1, a2, a3, etc. If all are also integers, then it's a algebraic Lafontaine equation. Now, whether the equation 2 has a solution or not. If this equation 2 has a solution, then how many solutions are there? It may possible that there is only one solution. It may also possible that there is more than one solution. Now, for a simple equation, let me write a linear algebraic equation. Say a1 x1, a2 x2 plus a3 x3, say b. Here there are three variables. One is x1, x2, and x3. These are three variables. So if we solve these equations, then it may possible that we may get a single solution. Solution means that satisfies this particular equation, or it may have more than one solution. More than one solution, again, when it is more than one solution, there may be two criteria, two conditions, or two classification. One is finite number of solution and infinite number of solution. For example, if I write this equation a1x is equal to b, then obviously this equation has a single solution. And similarly, if I write a1x plus a2b, a2y, that is equal to say c, then we know that this is a straight line, and this has got an infinite number of solutions. For a particular value of x, we'll have value of y. For a particular value of another value of x, we'll have another value of y. So this particular equation has a infinite number of solutions, but whereas this equation has got only one solution. But in some situation, we may or may not have solutions. And Lafontaine equation, in these equations, we are also interested in the solutions of equations. And in Olympiad examination, what we have general trend or the equations that what we have seen, that is asked the integral solution. That is, what is the integral value? The integral value means the x1, the solution set, say here x1 for this particular equation. So this equation, this one, equation number 3, for this equation, what are the integral solution of this equation number 3? That is, the solution will be obviously this is a solution set x1, x2, x3. This is a solution set. For the solution set, if all the solutions are integers, then we call this is the integral solution. If they belongs to Z, say dash a particular solution, dash, let me call this dash because these are variables. So this is a particular solution. If x1 dash, x2 dash, and x3 dash, no, this is your Z3. Z3 means all this, these are integral, these are integers. So we are interested in integral solution of equation number 3 in a particularly, or in general, the equation number 2. So here we will try to solve few problems related to Lafontaine equation. Okay, I have erased the screen, and let me take a very simple example. Now, before solving this, now what are the different types of solutions? There are, Lafontaine equation is a very complicated one. We have seen when the number of variables go on increase. When we know that in class 8 probably, or in class 7, we have solved this equation, say ax I'm sorry, there is some technical issues here. Okay. So as you have just I have mentioned, that for this equation, say ax that is equal to b, this is a very simple problem and the solution is unique. But when we increase the number, say this is another equation, a to y is equal to say b. So we have been now there are two variables. So if the number of variables go on increase, and also if it's a linear equation, if it's a quadratic equation, or power of x is more higher power, higher order, then obviously the complexity of solution for this particular problem will go on increase. So how to solve this type of equation? Now, based on the equations, we'll have to adopt a particular method to solve the equations. Now, one of the popular method is a decomposition method. One of the method is decomposition method. Yes, there are few more methods. One is known as modular method. Modular method, where we take the mode used in the concept of number theory. Then there are mathematical induction. Fermat's infinite decomposition, Fermat's theorem, and there are many more. So here today in my discussion, I will try to concentrate on decomposition method particularly, and if time permits, then I'll discuss a little more about this. Now, what is decomposition method? For try to understand this particular. Now, let me go back to the original problem. That is f. F is a function of x1, x2, xn, that is equal to say 0. It may be 0 or maybe say any other constant. Now, if it is possible to express this equation in such a way that say f1, x1, x2, xn, f2, x1, etc., and then f3 up to say f of k, x1, x2, xn equal to 0. So if it is possible to factorize this particular function in this form, that is f1, f2, f3, these are functions of x1, x2, etc. If it is possible to express this one, then if you can see that product of these three functions is equal to 0, then what can we say? Any of these functions must be equal to 0. Then only the product of few functions will be equal to 0. So this is one of the aspects. So we will try to proceed. In other words, if now decomposition or the factorization, sometimes it may be possible and sometimes it may not be possible. So for those problems where the decomposition will be simpler one and the possible, then how to approach for the solution of this type of problems, then we will go in that way. Now, in order to understand this decomposition method in a more better way, let us take a simple example so that you can understand the process of the solution process. So x square plus 1, say y square plus 1 plus 2 x minus 1 x minus y 1 minus xy is equals to 4 1 plus xy. Now this is an equation you can see, and we are interested for integral solution. We are interested for integral solution, or all integral solution. That means we'll try to find all integral solution for this equation. That is, what are the integer value of or integral values of x and y that satisfy this particular equation. Now, decomposition, as I have just mentioned, we'll try to express this function. First of all, we will try to search the product of few functions, so sub functions. So we can write in this way. This particular equation can be simplified. First of all, we'll have to simplify it so that we can put it into a product of different functions. If you expand this, then we'll have x square y square plus x square plus y square plus 1, and then plus twice x minus x square y, 2 is there, and then minus twice y, and then plus twice x y square. This is equals to 4 plus 4 xy. Now, obviously, now how to simplify? We have, first of all, we have to observe the terms, and we'll try to manipulate the terms in such a way that we can put it some common terms. So here I can do one thing, xy whole square, then minus say twice xy plus 1. Here twice x1 can be adjusted from this particular term, and we'll see later on if we can proceed in this way. Similarly, this x1, this one what I have settled here. Now this one x square, and then say plus y square, then minus twice xy. So this 4xy is adjusted with this minus xy, this minus xy. This first 3 terms is also adjusted. And now we'll see what are the terms left out, and if we can do anything similar to this one. So obviously, if we take these 3 terms, then it is x minus y, xy minus 1 whole square. This will be x minus y whole square. And for this one, we can this particular term and this particular term, this can be written as twice x minus y, and the rest 2 terms, that is what can we write, is minus 2, that is from this term, and from this term what can you write, minus 2 x of y, that is equal to x minus y, and that is equal to 4. So if you further simplify, then what can you write? This is your xy minus 1 whole square, and this is x minus y whole square, and this will be plus 2 x minus y, and then minus 2 xy, x minus y, and that is equal to 4. So now I can take x minus y can be taken common from this term, and from this term, and from this term. So let me take common. So xy minus 1 whole square plus x minus y, let us take common. Then what we'll have? We'll have here x minus y plus 2, and then minus twice xy, minus twice xy. Or what can we see that? Or let me know little x minus y square. Now these particular two terms can be written in this way: twice x minus y into 1 minus xy. 1 minus xy, that is equal to 4. Now if you observe these first 3 terms very carefully, you can see that this is whole square. So this is another term square plus 2, the second term, this one, and this one is the first term. Since it is x minus y, we can make it minus. We can adjust this particular 2 terms and take a negative sign here, so that I can put in this particular manner. So what can I put is that xy minus 1 whole square plus x minus y whole square minus twice xy minus 1, and then x minus y, that is equal to 4. So a square plus b square minus 2ab. So now what can you write is that a minus b, that is x minus y whole square, that is equal to 4. Whole square, that is equal to 4. So now this particular inside term can also be simplified. Let me wrap these portions. Where we left, or if we further simplify this, then what can you write? You can simply write that let us know x y minus 1 minus x plus y whole square, that is equal to 4. This is, x can be taken common. So here, what from this term and this term, x can be taken common. So what we'll have? We'll have x, that is y minus 1. And from these two terms, what can you write? Minus 1 is common, or no, we can take plus, so y minus 1. So what can you write? Y minus 1 x plus 1 whole square is equal to 4. Yes. Now we will now use the concept of how to solve. Now this is a simplification. For this first problem, I have detail shown that how to factorize the terms. Now depending upon the different equations, this particular technique of factorization will be obviously be different. Now here for this particular problem, now at this stage, what we have seen that square of sub quantity is equal to 4, and here we are interested for integral solution. Here we are interested for integral solution. That means the value of x and y are integers. So now if this is product square is equal to 4, then obviously if we take the square root of this one, then we will have x plus 1, that is equal to plus minus 2. Now there may be different possibilities. Now let us see, since x and y are to be integers, so this quantity y minus 1 and x plus 1 are also to be integers. So what are the different integral values of this quantity and integral value of this quantity that satisfy plus minus 2? It may possible if we take y minus 1 is equals to say plus 2, then what will be the another term? The other term may be other term will be obviously the x plus 1, that is equals to 1, so that the product of this become plus 2. Again, y minus 1 can also be equal to minus 2, because this particular term y negative minus 2 is also there, possibility is also there. So if I take y is equals to a minus 2, then I can put x plus 1, that is equals to I can take 1 as well. In that case, the product will be equal to minus 1. I can also take y minus 1, that is equals to 2, y minus 1, that is equals to 2, and x plus 1, that will be equal to minus 1, so that the product is minus 2. Now how many possible cases will be there? How many possible cases will be there? Now to make it simple, let us write in this way, that we will take the cases when the product is equals to 2. When we take the product is 2 plus 2. That is, one is plus 2, another is minus 2. So for plus 2, this one case is this one. The next case is y minus 1 is equals to, if I take this is negative 2, then x plus 1, that will be equal to positive. This is also negative 1. Now if I take y minus 1, that is equals to plus 1, then x plus 1, that will be equal to 2. If I take y equal to y minus 1, that is equal to minus 1, then x plus 1, that will be equal to minus 2. Now these are the only 4 cases when this product is equal to plus 2. This product is equal to plus 2. Okay, one is plus 2, this is for product is equal to plus 2. These are the only 4 cases. Now if this again, if the product is equal to minus 2, if the product is equal to minus 2, then what will have? For product is equal to minus 2, what will have? We will have, we can write the similar for situation. Say this is equal to minus 2, then obviously x plus 1 will be equal to plus 1, so that the product is minus 2. Similarly, when I take x y minus is equal to plus 2, then I will have to take equal to minus 1, so that the product is minus 1. Similarly, y minus 1 is equals to, now again we can take 1, so that x plus 1, that will be minus 2. And one more case, that is y minus 1, that is equal to, what is it? Yes, minus 1, then x plus 1, that is equals to 2. Now here in all these cases the product is minus 2, and here all the cases the product is plus 2. This is plus 2 and minus 2. So 8 different cases. In other words, we can say that we will have 8 solutions. Now if we are not interested for integral solution, then we cannot conclude like this. For integral solutions only we can put in this way. Now obviously there are 8 cases, so we can say that how many solutions are there? There are 8 solutions, but we are interested for the solutions of x and y, for the values of x and y, but here they are not x and y. So further we'll have to write one more line. Now this particular line, this particular 4 cases will gives us xy in xy. Now what are the 4 cases? The first cases will gives, here y equals to 3. If I bring this one in the right hand side, we'll have 3, and this one will neutralize this one. So 3, 0 is a solution. Similarly, for this one, for this second set, we'll have the solution minus 1 and minus 2. We have solution minus 1. Sorry, I have written in reverse order. I'm sorry. Here x is first, so this value of x is first. I have to write here. So x is equal to 0, and then y is equal to minus 3. So I have written x first, so I have to write the value of x first. So x is equal to 0, and then the value of y is equal to 3. And the second case, here the value of x will be equal to minus 2, and here the y is equal to minus 1. So the next value is minus 2 and then 1. Sorry, minus 2 and the minus 2 and minus 1. Minus 2 and minus 1. Similarly, for the third, this particular third set will gives us x is equal to plus 1 and y is equal to plus 2. X is equal to plus 1 and y is equal to plus 2. The fourth case will gives us x is equal to minus 1, and y is equals to what? 0. Y equal to 0. So these are the 4 sets of solutions for the first cases, and for this case, for this particular cases, will gives us x y. This pair will gives us the value of x is 0 here, and the value of y equals to minus 1. So it is 0, minus 1, and for this case we'll have the solution minus 2 and then 1. Minus 2 and then 1. Similarly, this set will gives us minus 3 and then minus 2, minus 3, minus 2, and the fourth one will gives us the value 1 and then 0. 1 and then 0. So what are the solutions? These all 8 cases, these all 8 pairs are the solution of the original given equation. I have already wrapped the equation. I think this file is recorded, so anyone can see the solution. Obviously, the original, the video may be back forward, and then can be seen the original equation. So these 8 pairs are the integral solution of the given equation. So this is the process of solution for Diophantine equation. One of the key point here is this particular concept. The product of two terms is equal to plus minus 2, or if I can also write that y minus 1 Here the equation is y minus 1 and x plus 1, that is equal to 2 and minus 2. Okay, this is the equation. This is the derived form. So here we'll have to understand what are the possible cases. So how many solutions are there? This will give some hint. So how many possible solutions will be there? So this is the solution of this type of this particular first problem. Let me let me discuss one more problem. Now, before going to the next problem, if any query is there, or if the way how I am teaching or how I am discussing is this okay, or any I need to change my way of discussion, then also you can share. If I do not have any message from you, I'll continue as it is. If any query is there, then anyone can raise. I'm asking the students only, especially. Okay, since I have not received any query or any response, so let me continue in this session. Let me wrap this one. Okay. So now let us discuss a different problem. Let us discuss a different problem, or the method may be slightly different. Here, for this problem, say the problem is an example. Say x cube plus y cube, that is equal to x plus y whole square. Find all integer solution. We are interested for integral solution. We'll try to find the integral solution for this equation. What are the integral solutions of this equation? Obviously, similar to the previous problem, we'll have to rearrange the terms. We will have to factorize the terms so that the product of the terms, product of the functions, may be equated to some constant. Constant means some integer. So in order to do this, we have to manipulate the terms, obviously. So solution, we'll try to solve this problem. So solution is now this particular problem can be written as x cube plus, okay, let me write it once, x cube y cube x plus y whole square. Now this can be written as x plus y whole cube minus 3xy, and then x plus y. This is your x plus y whole square. So while doing this, what can we see that x plus 1, x plus y is coming common from all the terms. So this is how we need to try to adjust the terms or manipulate the terms. So from the three terms, all the three terms, or let me bring this from the left hand side. I can skip, but for the students, let me write one more extra step. 3xy, x plus y, then minus x plus y whole square, that is equal to 0. So now I can take common x plus y from all the terms, all the three terms. But we'll have x plus y whole square, and then second term will gives us minus thrice xy, and the third term will gives us x plus y, and that is equal to 0. If I now x plus y, okay, now what about the terms inside this bracket? These terms can also be, we'll try to express this term in a more simplified way, like in the previous problem. So if I expand this one and then adjust this term, then we'll have x square plus y square, then plus twice xy, and then minus twice xy. I can directly write minus xy, and then these terms will give us x minus y equal to 0. Now, Next objective is to express this in a product of some functions or in some simplified way. So in the right hand side, it is still equal to 0. So one way may be that this term, either this term or this term will be equal to obviously 0. Now how to deal with then these particular terms? That the term inside this bracket is also not so simple. How we'll conclude this one? So we'll try to further simplify the term inside the bracket, second bracket. So let me write in this way: twice x square plus twice y square minus twice xy minus twice x minus twice y whole bracket 1 by 2, and that is equal to 0. So what I have done, I have multiplied 2 in all with all the terms and taken 1 by 2 as common. So these terms can be adjusted. This term can be adjusted. So what can I write now is that x plus y. Now as similar to the previous problem, we'll try to express this. Let me write here x square, and then from the second term we can write y square, and this twice xy is already there, twice xy. Now we have adjusted this x square once, y square once, and we are left out, obviously we are left out 1 x square, 1 y square, and then we'll have to adjust with these terms. So let me write here x square minus twice x, this x square, another x square, we have written it here, okay, and then 1 y square is also left out, so y square minus twice y left, this, yeah, okay, so this is equal to 0, because this 1 by 2 is multiplied with all the terms, so I can know this 1 by 2 can be brought on the right hand side. So x plus 1. Now let us see how we can manipulate the terms inside the bracket. So obviously the 3 terms will give us x minus y whole square. These 2 terms will give us x. If I take x as common, yes, I can also do one thing. I can write down x is square minus twice x plus 1 and then minus 1. So this term, similarly, I can write, or I can write in this way. I can also write directly. I think the student will understand if I write in this way as well. X minus 1 whole square, then it is x square minus twice x plus 1. So I'll have to take 1 minus negative. Okay. To skip one more step, actually, I have written in this way. Similarly, these 2 terms can be written as y minus 1 whole square and then minus 1, because it will give us y square and then minus twice y and then plus 1. So a negative 1 has to be written here, equal to 0. So now the simplification become x plus y, and this become x minus y square, x minus 1 square, and then y minus 1 square minus 2, and this is equal to 0. So now we can conclude one thing. What can you conclude is that the product of 2 term is 0, and also these 2 terms, though they are an individual term, but little bit simplified one, a particular pattern is following. Now we can conclude that this product of these 2 terms is equal to 0 means either x plus y equal to 0, either, or both may also be equal to 0. There is no hard and fast rule that one has to be 0. Both may also be equal to 0. So either this equal to 0, or obviously, or x minus 1, the other term, it is this one, plus x minus 1 plus y minus 1 minus 2 equal to 0. Okay, so this minus 2 equal to 0. Now I can bring this 2 in the right hand side. So how can I write in this way? We can write directly plus 2, right? This 2 is we have written here in the right hand side. So now there are 2 cases. One is x plus 2. Let me know x plus y is equal to 0, or this is equal to 0. Now if x plus, what is the meaning of x plus y equal to 0? Now what is the meaning of x plus y is equal to 0? Now if x plus y equal to 0, if x plus y equal to 0, then what are the integral solution for what value of x and what value of y? This will be equal to 0. Obviously, we are interested for integral solution. Probably you can recall that initially I have written one equation ax, a1x, and then say a2y is equal to say some c1. Okay, this is a straight line I have mentioned, and this is a particular case of this equation only, where a1 is equal to 1, b1, a2 is equal to 1, and c1 is equal to 0. So this is a straight line, obviously, and there are infinite solutions. For example, if I take x is equal to 1, then obviously y will be equal to minus 1, so that this is equal to 0. If I take x is equal to minus 5, then y is equal to plus 5. So the solution of this line can be written as x comma y, that is a pair of solution, can be written as k, or instead of k, let me write here n. Okay, let me write here k and then minus k, where k belongs to integer. Where z here, this particular symbol is for set of integers. Most of you know actually, but those who do not know, let me tell you that this is the symbol z. The simple z you can write in this way, the simple z, and then you can write in this way. So what is the solution of this equation? Solution of this equation can be written in this form. That if x is equal to k, then y equal to minus k, where k is an integer. K is any integer. K may be 1, 2, 1000 or minus 10,000. Now here k may be plus or minus. So if x is equal to plus 5, then y is equal to minus 5. If x is equal to minus 3, then y is equal to plus 3, and so on. So this is there. How many solutions are there? There are infinite number of solutions for this part of the equation. Now what about the other part? Now if suppose x is not equal to 1, suppose x is not equal to minus y, or suppose x plus y is not equal to 0. Okay, if this is not equal to 0, then we are bound to say that this part must be equal to 0. That is, this part must be equal to 0, or this equation follows. Let me mark here, this is equation number 1, and this is equation number 2. So if x1 so if x plus y is not equal to 0, then this must be equal to 0. So what if this is equal to 0? The second part is equal to 0. The second equation is equal to 0. That is x minus y whole square plus x minus 1 whole square plus y minus 1 whole square, and that is equals to 2. Now the analysis, we have to analyze. Well, two part of this problem is that one, first of all, we have to factorize the terms, and second, we'll have to analyze the terms. Now in this analysis process, you can also see that we have taken x is not equal to 1, and the solutions are integers. Now observe the individual term. This is a perfect square number. This is a perfect square number. This is a square number, and this is also a square number. So it's 3 square number, and sum of these 3 numbers is equal to 2. Sum of these 3 numbers is equal to 2. So what are the possibilities here? So it is obvious that if this is one of them, it must be an integer. If all of them are equal to at least 1, since they are integers, so their summation or their difference is also an integer. So if all of them are at least equal to 1, because square term can never be negative, so at least minimum value of this is equal to 1, minimum value of this is equal to 1, and minimum value of this is equal to 1, and sum of all these values is equal to 3, and the right answer is 2. So it is not possible. So it is not possible that all these 3 terms are not equal to 0. It is obvious that at least one of them must be equal to 0. Okay, it is not 1. There may be 2 terms. Say this is equal to 2. Yeah, only one term must be equal to 0 at the same time. Because if I take this is equal to 0 or this is equal to 0 for a particular case, for an example, then this has to be equals to 2. Now, what is an integer number? The square of that number is equal to 2. Is it possible that if there is any number, the square of that number is equal to 2, an integer number? No. So obviously, only one term is equal to 0, and the other term, both other rest of the terms will be equal to 1. So this is one of the analysis how to approach for the solution. Now let me tell you also one more thing. for Olympiad problem, we will have a sufficient number to deal with this type of problems. So it is in Olympiad examination, type of examination, you need not concentrate all the problems at the beginning. If you can solve all the problems, then it is quite okay. But if you categorically select few problems that you can deal with, and you can certainly find the solution. And also one more thing, your process should be correct. Sometimes the solution may not be, it may not be possible for you to complete the solution. But whatever, if your process is correct, then you'll also credit some marks for that. So okay, so you need to you need to devote some time to understand the problem first, and then you try to deal with the problem, try to solve the problem. So this is just the analysis that I have just made. Now, so from this equation, we must have a situation where we can say that x minus 1, this particular quantity, is either less or equal to 1, and y minus 1 will obviously be equal to less than or equal to 1, because none of this number can be equal to 2 or more than 2, and they may be integer only. So less than 1 means what? Either this is 0 or 1. This is the only options. Again, this is also equal to 0 or 1, and similarly for this one as well, for this one as well. Okay, let us concentrate for these two terms. This will automatically give you the value of x and y, and that will adjust in this particular term here. So what this gives you? What this particular first left hand side inequality, this is known as inequality. I hope that all of you have the idea of inequality. Now here, this particular means this inequality can be further extended in this way, that okay, let me write one more step. This can be written in this way, that okay, so I can write in this way. Okay, so minus 1, x minus 1 is less than or equal to 1, because mode of this is mode of square that is equal to less than 1. So x minus 1 will be less than or equal to, you can write in this way, right? In this particular term, let me write, this particular term can be written as x minus 1, those who understand modulus. So this is given by less than 1 or equal to 1. Okay, so product of this x minus 1 and x minus 1 is less than equal. So this particular term can be written as in this particular form. Similarly, we will have this particular term can also be written in the similar phrase. Okay, so let me write down here. So this is minus 1, y minus 1. I have missed something. Oh, no, it's okay. It's okay. So this is equals to plus 1. So the left hand side inequality will gives us, we bring this one in this particular one. So we'll have, or if we add 1 in all the terms, then we'll have 0 here in the left hand side. This one will be cancelled out, and this will be equal to 2. Equality is also there. Equality is also there. And the right hand side inequality, this particular inequality will gives us possible is y, and then 2, right? And then 2. So in other words, the value of x will be from 0 to 2, and the value of y will also be equal to from will take from 0 to 2. Then there are only 3 possibilities. One is x is equal to 0, x is equal to 1, and x is equal to 2. Here also we'll have the similar cases. So now, if x is equal to 0, then we will try to see what are the others, what is the value of y. So if we try to substitute the value of x is equal to 0 in equation number 2, this is the equation number 2. I have rewritten this equation. So let me mark this equation 2 only. Okay, this is equation number 2. So if x is equal to 0, if we substitute there in this equation number 2, then what we'll have? If x is equal to 0, then we'll have y square. This is your y square. And then x is equal to 2 means this is equal to 1. 0 is 1. X0 means this is equal to 1 square means 1. And then plus y square, plus y minus 1 square, that is equals to 2. So this particular second part will gives us a situation where if you want to further expand this one, so this one will bring in the right hand side. So y square minus twice y plus 1 that is equal to 1. This 1 means this plus 2 and this 1. Okay. So now what we have seen, twice y square minus twice y, and that is equal to 0. This one is adjusted with this one. So what we have seen, that y square minus y equal to 0, and then you can write y minus 1, and that is equal to 0. So what we have seen is that now y may be equal to 0, and y may be equal to if this part we consider, this is y equal to 0, and for this part we'll have y equal to what? Plus 1. So for x is equal to 0, we have these two cases, that y equal to 0 or y equal to 1. But note it, at the very beginning, for x is equal to x and y are equal, for the first case, when this one, in this case when we took that x plus y equal to 0, so if both x is equal to 0 and y equal to 0, then obviously this will be equal to 0. So when x is equal to 0 and y is also equal to 0, this will fall in the first case only. This will fall in the first case only, because k is an integer here. So we can ignore the first part of the solution. The second part of the solution, that is x is equal to 0 and y equal to 1. So x is equal to 0 and y equal to 1 is another solution. Is a solution. Okay. So similarly, for x is equal to 1, since x takes belong from 0 to 2, x is equal to 0, x is equal to 1, and x is equal to 2 are the three cases. So for 0, y equal to 1. For x is equal to 1 and 2, we can proceed in similar fashion. I think that I need not to go, but under the similar discussion, we can solve this. Okay. So similarly, if we try to solve these equations, that is for x is equal to 1, what are the values of y? Similarly, for x is equal to 2, what are the values of y? You can also try to find the solution. Okay, this is for students. For x is equal to 1 and for x is equal to 2, what are the solutions? Now let me write down the solution so that you can work out at your home. So when x is equal to 1, then y may be equal to 0. This y may be equal to 0. This is 0. This is a pair of x, y. And when x is equal to 1, we'll have one more solution, that is equal to 2. For x is equal to 2, one solution will be 2, 1, that is y is equal to 1 is a case, and then x is equal to 2, then y is equal to 2 is also another solution. So this for this case we will have two solutions. For x is equal to 2, we will have two solutions. So how many solutions? Already there are infinite number of solutions. One pattern is that one is k, another is minus k, and there are 5 different types. One is 0, 1, 1, 0. To show complete solution, let me write down the complete solution. One is k minus k, where k belongs to z. This is one, infinite number of solution is there. Next solution is 0, 1. Next one is this one, 1, 0, 1, 2, and then 2, 1, and then 2, 2. So these are the solution set. This is the solution set for the given problem. Now for suppose in a examination, suppose we are in by some ignorance or some by lack of understanding of the problem, if we cannot find all the problem but partial solution if you obtain, then also you can deserve partial mark in the examination. So this problem may be a lengthier one, but the importance of the problem is also cannot be ignored, and this type of problems are also asked in the examination. So this is the thing. So till this discussion, I have discussed only two problems, but in elaborately more, I have taken some extra time maybe so that the student can understand smoothly. Till now, if any query is there, then anyone can raise for integral solution. Go a little fast. Okay, someone has mentioned that we'll go a little fast. Okay, I'll go. Okay, now this is another way of solving a particular problem. Now let me take one more problem. This is will be problem. This one will be slightly different. Okay, let me take one more problem. So let us consider this problem 1 by x plus 1 by y is equals to 1 by z. How to solve this problem? That is, we are interested for integral solution and say positive integral solution. We are interested for positive integral solution. That is, the values of x, y, and z all will take the positive values only. Okay. Now, how to solve these equations where x, y, z, for what are the integral values of x and y, x, y, z, so that this equation is this. This equation can be simplified xy y plus x that is equals to 1 by z, or we can write z that is equals to xy x plus y. Say mark this equation. Now let d equal to GCD of x and y. As I have come to know that probably you are familiar with this, little bit about GCD and all, and their symbols, notations. You are familiar about this. So let us take GCD of this x and y be x comma be d. Then we can write down that x can be written as some d is multiplied some m, and y can be written as d multiplied by some n, where m and n these are some integer. Obviously, here we are discussing for positive values, so this is natural number. Or since x, y all in positive integer, so x comma y are integers, and also m comma n GCD of m comma n equals to 1. This is also another condition for this one. So now if this is so, then this will also imply that GCD of m plus n mn this also equals to 1. This is another property, or if you can slightly think about this, you will understand this also satisfies the same. If GCD of mn is equal to 1, then GCD of m plus n and mn equal to 1. So now we will try to use this concept in this equation number 1. Now let us see here. Equation number 1 can can be written as z is equals to x is equals to what? dm, and y is equal to dn. So dm into dn, and denominator x plus y is your dm plus dn. Further simplifying will gives us d of m, d into mn, and d is m plus n. Now since GCD of this is equals to 1, GCD of this is equal to 1, so this will gives us that GCD of this, GCD of mn GCD of this is equal to 1 means this GCD of this and GCD of this is equal to this 1. That means what? They do not have any common factors. They do not have any common factors. So, and also Z is an integer. Z is an integer. So from this, that the GCD of this part and this part is equal to 1, and Z is an integer. So what can we must say that M plus N, this quantity must divide D. If this particular quantity divides this particular D and that is an integer, then only their product will be an integer. Otherwise it is not. So this particular M plus N must divide this D. So that can, what can you write that in this notation that M plus N divides D. So this particular, this is a symbolical notation, and this symbolical notation can be written as D that is equal to some K into M plus N. K into M plus N. What is M? M, N all are natural numbers. Okay. Yeah, and K is also a natural number. K is also a natural number. I must write that K belongs to. Now, instead of natural number, let me take Z. Instead of natural number, let me take Z. I'll let you know why I have taken Z instead of N. Z is a set of integers and N is a set of natural numbers. Now, from this equation, the D is taken as this one. Now, what is the solution? The solution accordingly, this is the solution that we have to assume that X that is equals to D into M. And what is D? D is equal to this one. And M is obviously an integer, N is an integer, N is an integer. So what can we write? That D is K M plus N into M, or more simplified, say K M plus N. M plus N. This is your X. And what is Y? Y equals to Y is equals to here Dn. So D is given by K M plus N into N, that is equals to K N M plus N. Now, as I have mentioned that M, N, and then K are all integers, are all in integers. So you can see, so suppose for a situation when M is equal to 0, if M is equal to 0, then this quantity will be equal to 0. If M is negative quantity and K is negative quantity, then this is a positive quantity. This is a positive quantity. So depending on the value of M and N, there is a possibility that M may be negative, K may be negative, but these as a whole, as a whole, this the product is positive. So this is a solution where M, N, and K belongs to Z, provided that they are positive, provided that K into M plus N is positive. One example may be K is equal to -1, M is equal to -1, and N is equal to 4. N is equal to 4. So this may be a solution. This may be a solution for this particular here, for this one. Okay. So I think K. Okay, no, this condition will not be hold, because let me explain once again. When we take either of them is greater to this one. In other words, this condition will not be correct. So K, M, N all are set of integer. I try to show if there is any possibility that either of them is integer, but no. If they are integer, then any one of them will be negative. So all these are belongs to set of natural numbers. Finally, we can take here it is Z. We do not have any problem. But finally, since our solution is positive, so finally we can have this that since X and Y are greater than 0 according to the assumption that we are interested for integral solution. That is why we can write down K, M, and all are integers. So what is the solution? This is the solution. This is the solution for M and K greater than all integers. Okay. So till now, is there any query?
Abhigyan, any query? He's from 9. Abhigyan, I think.
Okay.
It's okay. Have you got why D is why X is assumed to be GCD? Sorry, D is GCD to be XY, and have you got that step?
Yes.
Okay.
Okay, so if you understood that, it's quite okay. I'm in little slow because I do not know the capacity of different students. There may be students where very lower level as well.
The
It's
problem,
better
sir.
to
This one is
yes,
excellent. This is a
okay.
more problem.
Yes. But for this we need some basic concept as well. Okay. So so this we have also seen that this particular this division or LCM kind of thing, GCD, this concept is applicable in many problems. So if you have a very good knowledge about this, then it is very good. Okay, now just take one more problem of the similar type. To conclude, I will not take so much time. Let us take a simple problem, that is how to deal with. Let us consider that x square y minus 1 y square x minus 1 equal to 1. Now this problem was where asked, this particular problem was asked in an Polish Mathematics Olympiad. And I think the problems I had discussed, probably few of the first one or the second one was asked somewhere, some the mathematics Olympiad, I don't know the exact year of that. By the way, so how to solve this type of problem? Now, first of all, as I had mentioned earlier, that first thing is that we need to tackle or deal with the simplification part or the factorization part. Here, if I take x is equal to say u plus 1 and say y is equals to v plus 1, then substitute here, further simplify. To simplify will give you u plus v plus 4 u into v plus 1, and that is equal to 5. So this is the product of two term, and that is equal to 5. Now, what are the different types of solution? Here, obviously, since they are integers. So if they are integers, then there will be two cases. If this is equal to 1, then this must be equal to 5. If this is equal to 5, then this must be equal to 1. Another case is that if this is equal to minus 1, then this is equal to minus 5. And if this is equal to minus 5, then this is equal to minus 1. So show that their product is plus 5. Now there will be two equations and two unknowns. For example, let me consider this one. The first case, when u plus v plus 4 is this is equals to 1, and u into v plus 1, that is equals to 5. So there are two equations and two unknowns. U and v are the unknowns. For further, u plus v, that is equal to minus 3, and u into v, that is equal to 4. Now you can see the product of two number is 4, and their sum is minus 3. So what are the possible solution of this? So you can proceed. Is this correct? Yeah, okay. U plus v is equal to minus 3 and uv. So what are the possible solution for this type of thing? Now here, will we get any integral solution of this? Is there any possibility that we will get? Now for this, how to solve this one? We can also do one thing, say u minus v whole square. There is a technique of doing this. You can write u plus v whole square, right? U plus v whole square minus 4 uv. If we expand this, then it will be simplified. For this formula, you need not worry about. There is a formula you can see also in the book. So u plus v is equal to minus 3 minus 4 into uv, that is equal to 4. And so what we have obtained is 9 minus 16, and that is equal to minus 5. Sorry, say minus 7. Minus 7. So what we have seen that u minus v square that is equal to -7. Is it possible? There is no solution that the square term, when they are real term, square of real term can never be negative. So solution does not exist. No solution. No real solution, but since we are discussing in the real field only, so it is, you can directly say there is no solution of this where this condition satisfied. If we have the solution, we have to write down for example, take the second case. I'll wind up with this one. Okay, for the second case, okay, let me take here UV. Okay, yeah, I mean take a second case. U plus V plus 4 is equals to 5, and U into V plus 1, that is equals to 1. So what I have seen, U plus V, that is equals to 1, and U multiplied with V, that is equal to 0. Now product of two term is equal to 0, and sum of these two terms is equal to 1. Now there may possibility that either U is 0 or V is 0. If U is equal to 0, if U is 0, then V equal to 1. If V is 0, then obviously U is equals to 1. So this is a pair of solution. This is a pair of solution. This is one solution. This is another solution. These are the two solutions set. Similarly, these are the two cases. For one cases we do not have the solution. In the second case we have two solutions. Similarly, for the third case and fourth case, we will have few solutions. So collecting all the solutions will give us the solution. Now it is asking about the integral solution. Okay, now solution is integral solution here. Integral solution. Now there may be, question may also be like this. It may, the concept, there may be some question of this type, concept of this type, a positive solution. Positive integer. Positive integer. So if the integers are positive, then we cannot consider this is a solution, because one of the solution is not positive, one of the solution is not positive, and one of the solution is not positive. Neither of solution is acceptable under the given condition. So similarly, we'll have to think about the rest of the problem. There may or may not have solutions. Suppose we have, it is asked that non-zero solution or non-negative solution. For non-negative solution, this will considered as a solution. These two will be considered as a solution. Both of these will be solution, because it is non-negative. It is zero but non-negative. Okay, so depending on that, what is the question, whether it is for any integral value, it is positive integral value, or it is non-positive integral value, or non-negative integral value, that thing we'll have to we'll have to carefully, we'll have to observe very carefully. So this is what I think I do not want anymore. So any questions till now? If any query related to the topic, related to this particular problem, or the problem's complete problem, or about the topic, I will first at the very beginning, I'll ask the students especially.
Yes, children, you have any questions, queries on this? Sir, can you leave 2-3 questions here so that they can note down? Is it ready with you, sir?
Yeah, okay, I can.
Only the questions.
Yeah. Okay, yes, the student can practice by themselves. Actually, I have not discussed this particular problem where x is prime.
That's okay, sir. They will try.
Okay. Let me write down one or two. Now a hint to this particular problem. A hint how to solve it. Just I'm giving you the hint. It is asking to solve this problem for positive integral solution. That means you need to find the positive integer values of x, y, z, so that this equation is satisfied. Now it is to be understood, positive means x can never be 0. So its least value of x is equal to 1. Similarly, the least value of y equal to 1 and the least value of z is equal to 1. So if I take 1 in all the cases, x equal to 1, y equal to 1, and z is equal to 1, then sum is equal to 3. For example, left hand side sum is equal to 3. And the right hand side, what we have seen, this quantity is less than 1. This quantity is less than 1. In other words, this quantity can be written as 1 minus 2 by 5. 1 minus 2 by 5. So since this quantity, this quantity is less than 1. So if I take the least value of x, y, z, so it is greater than this quantity, so this is not equal. But also note that while we increase the value of x, the left hand side value will go on this 1 by x. So when we increase the value of x, then obviously 1 by x is go on decrease. Where is denominator? As you increase the denominator, then obviously the whole value will go on decrease. So we'll have to choose, obviously. So the value of x, y, and z, all of them cannot take the least value as a least value. They cannot take 1 at the beginning, or the least value of all this cannot be equal to 1 for all the variables. So what is the next possibility? Next possibility is if x remain 1, then if and y remain 1, if this is equal to 2, then what is the solution? So this way you will see that we will fix a particular value of x, say x is equal to 2, then what will be the solution
Sir,
for the
like we
remaining
need
part?
to take cases, I guess.
Can you please repeat?
Sir, like, do we need to take cases, something like that? I can say.
Yes. So for this case
Yes,
cannot be
yes.
gone infinite. It cannot go on infinite. So
Yes.
we'll try to find out the least value. So after certain value, say either x is equal to 1 and then greater than 1. That way, we have to play the cases.
Right, sir.
So this is a hint how to deal with this type of problem. This one only a little bit complicated one, B1, because I have not discussed. Complicated means since I have not discussed anything. So no prime number. You have the idea of prime number, but how to deal with this type of problem, there is a different case. So no, try to see if then you can try to find out any solution. Yeah. So I think I can stop at this level. And you
Yeah.
can also see the questions paper of, nowadays in internet will available all the questions paper from different Olympiad examinations.
Yes.
Yeah,
Yes.
try to solve this type of problems.